What happens when energy is added or removed to a substance? A substance often undergoes a change in temperature. However, not all transfer of energy results in a change in temperature. In this case, physical characteristics of the substance change from one form to another, commonly called as phase change. Today's topic is about phase change. What happens during phase change? When energy is either absorbed or released, it results to the change in the state of matter with unchanging temperature. We have to emphasize that during phase change, it's only the state or form of matter that is being changed, but the temperature of the substance remains the same. Here are the different phase changes. When solid absorbs energy, melting process will happen resulting to a liquid. Or, when solid absorbs energy, sublimation process will happen resulting to a gas. When liquid absorbs energy, vaporization process will happen resulting to a gas. When gas release energy, deposition process will happen resulting to solid. Or, when gas release energy, condensation process will happen resulting to a liquid. And when liquid release energy, freezing process will happen resulting to a solid. We know that a substance needs energy transfer or Q to change the phase of a certain mass or M of a substance. So this ratio of Q over M is an important thermal property of a substance which is called as latent heat or L. And latent heat is the heat that must be added or removed to a mass of substance to convert it from one phase to another without changing the temperature. From this definition of latent heat, we can derive the formula for energy transfer or Q, which is Q is equal to mass times the latent heat. The value of L or latent heat for a substance depends on the nature of phase change. So we will be using the terms latent heat of solidification if the phase change is from liquid to solid, latent heat of fusion if the phase change is from solid to liquid. Since solidification and fusion are reverse processes, therefore, the latent heat of fusion is equal to the latent heat of solidification. The negative sign will be used for energy leaving a system. Hence, our latent heat for solidification is negative because in solidification process, a liquid must release energy to become solid. Latent heat of condensation will be the term used for phase change of gas to liquid, and latent heat of vaporization is the term used for a phase change of liquid to gas. Latent heat of condensation is equal to the latent heat of vaporization because these two are reverse processes. Negative sign will be used also for latent heat of condensation because the gas must release energy to become a liquid. Let us have our first example problem. A 1 gram of ice initially at negative 30 degrees Celsius is converted to steam at 120 degrees Celsius. Calculate the total amount of heat involved in the process. Let us analyze the given situation. Since we are given an ice that must be converted to steam, we need the following values: the specific heat capacity of ice, water, and steam. And since the ice will undergo a phase change, therefore, we need the latent heat of fusion of ice and the latent heat of vaporization of water. Aside from this, the other given are mass of ice as 1 gram that must be converted to kilogram as 0.001 kilogram, the initial temperature of ice, which is negative 30 degrees Celsius, and the final temperature, which is already in steam, at 120 degrees Celsius. We are asked to compute for the total amount of heat, or Q total. So let us analyze this temperature versus energy graph. So our ice is initially at negative 30 degrees Celsius. So if it absorbs heat, our ice will increase its temperature to 0 degrees Celsius. And for it to happen, the ice needs an amount of energy transfer. We will name this as Q sub 1. And since this involves an increase in temperature of our ice, therefore our Q1 will be calculated as mc delta T of the ice. Once the ice reaches 0 degrees Celsius temperature, it is now ready to undergo phase change or melting process. And this melting process, for it to happen, it needs also another amount of heat. We will name it as Q sub 2. And this amount of heat, or Q2, is calculated as M, which is mass of the ice, times latent heat of fusion. Latent heat of fusion will be used because it is from solid going to a liquid state of matter. And once our ice melts, it will now have a temperature of 0 degrees Celsius, and it's now already in a liquid form. So our liquid, which is water at 0 degrees Celsius, must undergo an increase in temperature up to 100 degrees Celsius. And for that water to increase its temperature, we need another amount of heat. We will name that as Q sub 3. And Q sub 3 will be calculated using mc delta T for water. So this is already water, therefore our C will be the value for the water. And once our water reach 100 degrees Celsius, it is now ready to undergo phase change again. And that water will be transformed into the gaseous form, which is the steam. And we need another amount of heat for that phase change. We will name that as Q sub 4. And Q sub 4 is the amount of heat needed for the phase change of water to steam. And that's calculated using mass times latent heat of vaporization. Latent heat of vaporization, or L sub V, because this is a vaporization process wherein the water is converted to steam. And once our steam reach 100 degrees Celsius, it is now ready to increase its temperature. So for this part, we need another amount of heat, which is Q sub 5. And Q sub 5 is the amount of heat needed for our steam to increase its temperature up to 120 degrees Celsius. So therefore, our Q sub 5 is calculated as mc delta T for steam. We will be using specific heat capacity of the steam because this is already steam. And we are now ready for the substitution of our data. So let's start with Q sub 1. So to calculate for the amount of heat needed for the ice to change its temperature from negative 30 degrees Celsius to 0 degrees Celsius, we will be using mc delta T, which is the mass of ice, times the C, or specific heat capacity of ice, times the change in temperature, which is the final temperature as 0 minus initial temperature, which is negative 30 degrees Celsius. Calculating for Q sub 1, we will have 63 joule. Let's proceed with Q sub 2, which is the amount of heat needed for our ice to melt. So therefore, that is mass of our ice times the latent heat of fusion. So 0.001 kilogram times the value of L sub F for our ice. And this will give us 334 joule. For Q sub 3, this is the amount of heat to increase the temperature of the melted ice, which is already the water, from 0 degrees Celsius going to 100 degrees Celsius. That is why we are using mc delta T as our formula. By substitution, we have here the mass of ice times the specific heat capacity of water times the delta T of our water, which is the final temperature as 100 degrees Celsius minus initial temperature, which is 0 degrees Celsius. Calculating for Q3, we'll have 418.6 joule. Q sub 4 is the amount of heat again for phase change, and this phase change is from water going to steam. And therefore, we will be using the formula of mass times latent heat of vaporization. And by substitution, that is 0.001 kilogram times the value for L sub V for our water, and it will have a result of 2,260 joule. And for the last process, that is, we have our steam that is initially at 100 degrees Celsius going to its final temperature, which is 120 degrees Celsius. That is why for our Q sub 5, we have mc delta T as our formula, and by substitution, we have the mass, which is 0.001 kilogram times the specific heat capacity of steam times the change in temperature of the steam, which is 120 degrees Celsius minus initial temperature, which is 100 degrees Celsius. Computing for Q sub 5, we have 40.2 joule. And since we are looking for the amount of heat that is needed from our ice, which is negative 30 degrees Celsius, going to steam, which is 120 degrees Celsius, all we have to do is to add. So adding all of the value of our heat, we will get our final answer as the Q total is equal to 3,115.8 joule. Example problem number 2. 100 grams of water at 20 degrees Celsius are mixed with 20 grams of ice at 0 degrees Celsius in a calorimeter. Assuming that the calorimeter is of negligible thermal capacity, find the equilibrium temperature of the mixture. So let us analyze our problem. We are given here water and it is mixed with ice. So therefore, we need the specific heat capacity of water and the latent heat of fusion. Latent heat of fusion because our ice will melt. And aside from this, other given are the mass of water, which is 100 grams, the initial temperature of water, which is 20 degrees Celsius, the mass of our ice, which is 20 grams, and the initial temperature of ice, which is 0 degrees Celsius. Since it's stated here that the calorimeter is of negligible thermal capacity, therefore, we will not include calorimeter as part of our system. And we are asked for the equilibrium temperature of the mixture of our ice and water. So find T sub F. And since we have here water that will release heat for our ice to melt, therefore we will start our equation with negative Q loss equals positive Q gain. So by looking at the temperature of our two substances, the water has higher temperature. So therefore, the water will be the one to lose energy. So therefore, negative Q lost will be the negative mc delta T of the water. And the energy to be lost by water will be gained by the ice. And for that case, our ice will melt. So therefore, the Q gained is equal to the mass of ice times latent heat of fusion. So again, this is M times L sub F because our ice will gain energy and it will melt. Once melted, our ice will start to increase its temperature. So therefore, we will be also having plus mc delta T. So this is the mass of the melted ice times specific heat capacity of water since it's already melted times delta T. By substitution, we have here negative 100 grams times the specific heat capacity of water times delta T of water is final temperature, which is unknown, minus initial temperature of water, which is 20 degrees Celsius, equals, On the right side of our equation, we have the mass of ice as 20 grams times the value of the latent heat of fusion as 334 joule per gram, plus another amount of heat to be absorbed by the melted ice is 20 grams times specific heat capacity of water because it's already melted times the change in temperature of the melted ice, which is the final temp, minus 0 degrees Celsius. Simplifying our equation, we have here 100 times 4.186 will give us 418.6 joule per Celsius degree, and this is still multiplied to T sub F minus 20 degrees Celsius. On the right side of our equation, we have here 20 times 334 will give us 6,680 joule, plus 20 times 4.186 will give us 83.72 joule per Celsius degree, and this is still multiplied to T sub F minus 0 degree Celsius. We can still simplify our equation, so therefore 418.6 multiplied to T sub F and 418.6 multiplied also to negative 20 will give us positive 8,372. On the right side of our equation, we have here 6,680 joule plus simplifying 83.72 times T sub F, and 83.72 times 0 will still give us 0. So we will not write it anymore. Combining like terms, so negative 418.6 joule per Celsius degree times T sub F transpose 83.72 will give us negative 83.72 joule per Celsius degree times T sub F equals 6,680 joule transpose positive 8,372 joule will have minus 8,372 joule. Simplifying this will have negative 502.32 joule per Celsius degree times T sub F is equal to negative 1,692 joule. Since we are looking for the value of T sub F, we can divide both sides by 502.32, and it will have T sub F as 3.37 degrees Celsius. So again, this is the final temperature of our mixture when we put ice into the water. Example number 3. A 0.3 kilogram of ice at 0 degrees Celsius is placed in a liter of water at 20 degrees Celsius in an insulated container. Assuming no heat is lost to the container, how much ice will melt if the water will release the maximum amount of heat? So let's analyze our given. Since we have here ice that is placed in water, therefore the ice will melt, and we need the latent heat of fusion, and also we need the specific heat capacity of water. We're also given the mass of ice as 0.3 kilogram and its initial temperature at 0 degrees Celsius. And we are given also 1 liter of water, which is also equal to 1 kilogram of water in its mass, and the initial temperature of water is 20 degrees Celsius. Since no heat is lost to the container, we will not include the container as part of our system. And for this case, we are asked for the amount of ice that will melt, or the mass of the melted ice. And we are given the condition that the maximum amount of heat will be released by the water. So therefore, computing for the maximum amount of heat lost by the water, we will have Q of our water is equal to MC delta T, which by substitution will give us 1 kilogram of water as its mass times 4,186 joule per kilogram times Celsius degree as the specific heat capacity of water times the change in temperature of our water is 0 degrees Celsius minus 20 degrees Celsius. So 0 degrees Celsius is our final temperature because this is the temperature that the water must reach to lose its maximum amount of energy. And the initial temperature of our water is 20 degrees Celsius. computing for the amount of energy lost by the water, it will give us negative 83,720 joule. So let us see what is the amount of energy needed by our ice for it to melt. So in that case, we will be computing for the energy needed for our ice to melt it, that is mass of the ice times the latent heat of fusion. By substitution, we have 0.3 kilogram as the mass of the ice times the latent heat of fusion of ice. And it will give us an answer of 100,200 joule. The amount of energy lost by water, which is 83,720 joule, is less than the amount of energy needed to melt the ice. Therefore, we can now conclude that not all ice will melt. So to compute for the amount of ice that will melt, we will be using the formula of negative Q loss is equal to Q gained. So the amount of heat lost will be the energy lost by the water, which is negative mc delta T, and the amount of energy gained is the energy gained by our ice for it to melt, which is equal to mass of the ice times the latent heat of fusion. By substitution, we have negative 1 kilogram as the mass of water times 4,186 joule per kilogram times Celsius degree times the change in temperature of our water, which is 0 degrees Celsius minus 20 degrees Celsius, which is equal to the mass of our ice, which we don't know what is the value of that mass, times the latent heat of fusion. Simplifying this equation, we have 83,720 joule is equal to the mass times 3.34 times 10 raised to 5 joule per kilogram. Since we're looking for the mass and this m here is the mass of the ice that will melt, we will divide both sides by 3.34 times 10 raised to 5 joule per kilogram. And for that case, we can now compute for the value of m, which is the mass of our melted ice, as 0.251 kilogram. So 0.251 kilogram of ice will melt with the maximum amount of energy lost by water. You may now proceed in answering the assigned problem to your class.